we are looking at the assumptions that we need to make for the macro mechanics, and I think we covered these 4 assumptions. So you have to take this to a logical conclusion of what is the advantage of taking the fact that a CD exists, the strain energy density exists. So what does it lead to? So if you remember, we had defined the strain energy density as the energy per unit volume. U3D. And we had, by that time, we had also looked at how we could probably simplify using all of these. The stress, which was originally sigma 11, sigma 22, sigma 33, sigma 12, sigma 23, and sigma. So, because anyway, it's symmetric because of the no body moment situation that we had over there. And we also saw another way of writing the same thing, which I forgot to mention, is called as the white notation, where we are taking advantage of the fact that it is symmetric and therefore expressing it instead of a 3 by 3 symmetric matrix as a 6 by 1 column matrix. And in doing that, I also mentioned that the first 3 are quite clear: sigma 11, sigma 22, sigma 33, the way in which you order. And the next 3 you have by removing 1, then you remove 2,
3.
So you see that in this 1 is missing, this 2 is missing, and this 3 is missing. Another way of coming up with the same order is what White came up with, where he went through this diagonal, down the diagonal, and then back towards the first. So if you look at that same order, if you start with sigma 1, 1, 2, 2, 3, 3, 3, 2, 1, 3, and 1, 2 is what we get the same order as. So the same thing holds whether it is the stress or the strain as well, the same things hold. Now coming to the strain energy density, in the presence of, see, each of these we are not making as an independent assumption, so we are accumulating these assumptions. So starting with elastic, then when we say materially linear, we say what we mean is a linearly elastic material, and then we are saying in that linearly elastic material, no body moment. So in other words, amongst all the materials that are available, we are essentially shortlisting and coming with smaller and smaller subdomains which are of interest to us, because those are the kinds of materials anyway being used in flight vehicle structures or most structural applications for other non-aerospace applications as well. So that is essentially what we are moving towards. And this existence of the strain energy density, we talked about U3D, which is a function only of the gammas, and in the notation of what we had over here, where we call this as just sigma I, and for as an exception for the Latin indices, we say that I varies from 1 to 6 over here, so that we have those 6 elements covered over there. Same thing for the strain as well. So in terms of that particular notation, we had shortened our C, I, J, K, L, which was having I, J, K, and L only between 1 to 3, as instead of to just C, I, J. But always remember, when you're doing tensorial manipulation, etc., you have to go back to the original 4th order way of it, because this is essentially coming from a 4th order tensor, and the kind of rules that apply for its manipulation, etc., will be essentially those 4th order relationship. It's only for just simpler algebraic manipulations, we are bringing this, but this doesn't mean C has become a second order tensor like stress or strain, or nor for that matter that the stress and strain we will call gamma as well in a similar fashion. So neither have they become vectors. They continue to remain second rank, second order tensors, and it's just that for a matrix kind of a representation that we would like in a much simpler, compact way, we are trying to get in, use this particular notation introduced by Watt. Now, coming to U3D, therefore, earlier we were saying that it is equal toCijkl into gamma ij, gamma kl. But now, in the new notation that we have, we are just saying that this is equal to Cij into gamma I, gamma j. That's all that it is. Now, if you look at the Cij, it's because of this quadratic nature, it's very clear that if you take the derivative of U3D, let me start with let's say if I want to get Cij, it's very clear that the way I would do is I will do an experiment where I will plot the input is I, so I will say I have sigma I over here and a gamma j over here. I try to get certain points. I will join those points and essentially get the stiffness of that. So the slope of that, which will be 1 divided by that particular stiffness that I am interested in. So going by that same kind of a definition, and this is valid actually even if you have a nonlinear material, we can get what is known as a tangential stiffness matrix. So there of course the Cij will vary with the strain. So we are not bothering about that because we are interested only in the linear regime. So what we are saying is this particular strain is anyway done by plotting a particular stress component with a strain component. So this is nothing but your derivative of the sigma I with respect to gamma j. So that's what it is. And you can very easily see if you even expand that out, let's say the first row of that stiffness matrix, you will very easily see that sigma 1 1, or in other words sigma 1 is going to be given by a proportional term of all of the 6 strains, and each one of them will contribute a particular stiffness coefficient, and this is how that turns out to be. Now the sigma I in turn is nothing but the derivative of your strain energy density with respect to gamma I. Because remember, this is the net result, but this is what we had as the stress to start with, and that stress is what we replaced with this linear term. And so it's very clear that this is this Cij, which first can be written as a derivative of the strain stress with respect to the strain, can in turn, the stress can be replaced as a derivative of the strain energy density with respect to the strain, and therefore this is nothing but a second order derivative rho squared by dou gamma j dou gamma I of U3D. Now it's very easy to see that if I want the corresponding term in the matrix, which is either in the, if this is in the upper diagonal term, triangular term, you can look at the lower triangular term to check for the symmetry. Then you will see that your Cji is going to be given by the same process. It's just going to be the inverse of that. So it's going to be rho squared U3D by dou gamma I dou gamma j. Right? Because we are going to have it as partial derivative of sigma j with respect to gamma I, and sigma j you are going to replace it as partial derivative of the strain energy density with respect to gamma j, and once you do that you end up with this. Now if you compare these two right-hand sides, both of these are second derivatives of U3D. One is taking the derivative first with respect to gamma I, partial derivatives of course, and then with respect to gamma j. This is doing it in a reverse way. But that doesn't matter, as we know. The order of derivatives doesn't matter in a partial derivative, and therefore these two are equal to each other. In other words, your right-hand sides are equal to each other, which means that your left-hand sides are also going to be equal to each other. In other words, your Cij and Cji are equal to each other, and for the first time we have come up with what is called as a major symmetry. So we've been distinguishing this in the previous class, the minor symmetries versus the major symmetries. The minor symmetries resulted from the fact that the stress and the strain are symmetric, stress symmetric from this and strain symmetry from the very definition of the strain. We will look at a few typical definition of strains, or rather the most common one which is used in today's class. But essentially from those two, we saw that in this, your I and j became equal to, could be interchangeable, your k and l could be interchangeable. But now whatever we have come up with this is essentially saying that this as a pair can be replaced as well. So in other words, these two are interchangeable, which means that in your reduced notation Cij, your I and j are interchangeable over here, right? So now up to that point of the no body moment, we saw that the whole thing, what we call as the constitutive law relating the stress to the strain, had reduced to just a 6x6 matrix, which could be generally fully populated, may or may not be symmetric, but at that point, so we could say that there were 6 into 6, 36 constants that are associated with it, all independent of each other. But now that we have made this fourth assumption, in addition to those three, it's not independent, as again I'm stressing that fact, that you are adding up or accumulating these assumptions. So once you make this fourth assumption as well, then what happens is that 6x6 matrix now becomes symmetric. So your 6x6 matrix, that is your C matrix, is now known to be symmetric, and therefore it will have 6 diagonal terms and 15 off diagonal terms repeating themselves on the above and below the diagonal. So therefore 15 plus 6, you'll have only 21 independent constants. But in general, you could still have the full matrix fully populated. In other words, you will in general have 36 non-zero coefficients associated with it, but only 21 of them are independent, 6 being on the diagonal and 15 being off diagonal. So is this clear up to this point? Okay. So let's go on to the next assumption, that is of orthotropy. So yeah.
This existence of SCD, is there some case where this is not valid?
Yeah, good question there. So you see, the whole idea is that when you're doing some work on that through the application of a load or whatever kind of loads, it is undergoing certain change in size and shape, because of which it is storing potential energy, as we discussed last time, right? So now, in reality, what happens is that it's not only that which happens, there could be a heating which happens, for example. The material could get heated up. So in other words, there's a thermal dissipation. So there could be other forms of dissipation associated with friction and things like that. So all of these would mean that you cannot define the strain energy density the way you have defined. So it's not only about the existence of strain energy density, but the fact that all of the work that you're doing is getting into that particular mode, right? So you have to make sure that those dissipations are negligible. If it is not, then you have to bring in those aspects as well, and there could be a small asymmetry which could result due to that. So in all practical purposes that you will see, because we are only looking at this, already we have said linear, which means that the strain is already small. So now, once the strain is small, the deformations are small, and therefore the amount of energy that is getting dissipated in various forms is also typically negligible. So this is a reasonably good assumption to make. Also, when because as I said, we are making each one of these as a further subset. So as an accumulation, therefore, since we have already made this, there are certain things that are taken for granted, and this is more often than not, this is a valid assumption. But if you had, for example, an inelastic material, then it is possible that your strain energy density, because you have an elastic plastic regime, and you would have a certain hysteresis associated when you're, let's say, unloading the thing. So all of those will have to be accounted for. So you will not have this, it will still exist. It's not that it will not exist, but it not exist in the form that we have defined and taken advantage of to show the symmetry of the Cij matrix, right? Okay. So before we get on to orthotropy, maybe also I think you had asked another question about the strengths last time, right? So the strengths, whatever I described to you, is a valid answer as far as that at that point of time is concerned. But later on we will be going into the strength of the laminate itself. Okay, so there is a lot of research still going on in terms of how you determine that. There are certain things called the failure envelopes. So for example, the maximum stress or maximum strain, because you know that when there is a particular direction stress that is applied, there is a particular value at which it fails. But when you have more than one type of stress, or the same type normal stress but in two directions, what we call as a bidirectional loading, when you're trying to pull this way as well as that way, then it could fail at a stress level which is lower than each one of those maxima strengths that you had if they were unidirectional, right? So bidirectional could fail at a lower value of stress for each compared to the unidirectional. Now, there was an exercise called the worldwide failure exercise, which was conducted across the globe by a certain journal, and it went through 3 phases. It's known for short form as WWFV. So went through 3 phases, 1, 2, and 3. And some of the top leading researchers in composites participated in this. And to start with, they gave only a limited amount of data and asked the researchers as a challenge to predict certain failure values. And after that, the second level, they gave additional amount of information that was already available from the experimental tests, to see if they can come up with theoretical models which can be performing slightly better than what they had contributed in the first phase. And finally, they gave all of the data that was extracted out of the experiments, and then they asked them to improvise their material eventually. But essentially, most of them, what they ended up doing is curve fitting. So whatever kind of data that you have, you try to improvise on it better and better. So you see that obviously the third phase results turned out to be the best amongst them. But very few amongst them were phenomenological models. That, in other words, they take into account what is the phenomena physics involved in the actual way in which this material fails, and how it connects to other types of failure, and then all of them continue to propagate. So except for those phenomenological models, most of them turned out to be essentially curve fittings, because there's so much of uncertainty which is involved, which we also discussed in a previous class. So in terms of each of those individual fiber and matrix properties, and their volume fractions and their distribution, etc. So all of that contributes in terms of the failure, and you need a huge amount of statistical data to come up with something that kind of converges. And even then, to many of these problems, the physics-based phenomenological models are kind of elusive. There are quite a few phenomenological models, but still there is it's not conclusive, in the sense that there is more possibility of doing research in order to determine the strength. That's why we are not specifically teaching about the strength, because in any case we are dealing only with healthy structures. We are assuming that we are loading it in such a way that the stresses and strains are well within the failure limits, and therefore it can be analyzed that kind of a healthy structure. So because in any case the designer has taken the effort to make sure that it would not fail, and therefore we are in a safe regime. But there are extreme cases where we do need to take into account, and all of those will come into picture at that point of time. The other thing is when I reduced it from 9 into 9 into 9 into 6, I said that it is because of the strain being symmetric, which is essentially by definition. So again, there are exceptions to that rule as well. There are a few strains which are defined purposely in a non-symmetric fashion. Henke stress, for example, is a logarithmic stress which does that. There are quite a few others which do that for specific applications. But the one that we commonly use in most of our work is what is known as the Green-Lagrange strain, named after two mathematicians. Truly speaking, I'd have to introduce this in terms of a little more complex tensor analysis, in terms of what is known as a deformation gradient tensor, the transpose of that multiplied by itself minus I divided by 2. But it's a simple expression, so let me just write it. So this is how we would do, and this deformation gradient tensor, in order to introduce that, again it's a little more complex, because you would have to know what is known as a covariant basis vector and a contravariant basis vector. In Cartesian coordinate system, that doesn't make too much of a difference, where you have, let's say, x1, x2, x3 like this. So in such a system where you have unit normals defined along all of these, and they are mutually perpendicular to each other, the covariants and contravariants become identical to each other. But in most situations, you might want to deal with what are known as curvilinear coordinate systems, which are not necessarily orthogonal to each other, but they are not collinear. So you would have, let's say, y1, y2, y3 kind of a system over there. So in such a situation, so all of this is not part of your syllabus. I'm just trying to give you a flavor of what is typically done in more complex situations. So here, what you would typically do is be interested in the tangent to this for each one of these coordinate curves, and then the plane which is perpendicular to that particular tangent. And these could, though I've drawn it like this, these are spatial curves. They could be going in all directions. Essentially, they are not collinear with each other, but three distinct ones, using which, just like I can get one spatial point using x1, x2, x3, I can get the same spatial point referred to using the coordinate system y1, y2, y3. So when I have something like that, there are vectors that I define based on the position vector of material points, which are tangential to this, using that as the unit vector system. Then I get what are known as covariant bases. Similarly, when I use the basis associated with something which is perpendicular to those tangents, I get what is known as a contravariant basis vector. So typically what you do is you define a contravariant basis vector for the undeformed configuration. And
like,
oh, this power.
Yeah.
Okay. So
it is covered.
So we would have position vectors defined in the undeformed configuration, deformed configuration. We can derive those covariant basis vectors, contravariant basis vectors. In terms of that, we juxtapose them in essentially putting them next to each other, and therefore you get, instead of a vector, you get a dyadic, which is a second order tensor, very similar to your stress or strain, and from that you derive the gamma, like what we wrote, A transpose A minus I divided by 2. So that is what we would typically use in terms of defining it, but you are very familiar with the other simpler way in which you define the strain. let's say have a gamma ij defined as dou ui is a displacement in the xi direction. So this is how you would define linear strain, right? So once we say linear strain, in gamma and u, they are linear with respect to each other, and it's derivatives of u as well. And you also probably are familiar with adding a quadratic term to this whole thing, which we typically represent as dou um by dou xj, dou um by dou xi. Okay, so a quadratic term which goes with that, and like what we introduced, the Einstein summation convention, the m is something that summation is automatically done over each other, and the default value of ij and m going on from 1 to 3 is there in this as well. So now, if you look at this, this is quite symmetric, because if I interchange I and j, all that would happen is these two terms will get interchanged with each other. But whether you are adding a plus b or b plus a, because of the commutative nature of addition, that is going to give the same result, right? Because only j and I are getting interchanged, which means that will go here, this term will go here, and this term will go here. Similarly, you would see that these two will get interchanged with each other in the third term. So the product a into b would become b into a. So again, multiplication is also commutative, as we know, which means that very easily you can see that this particular definition, which is what is the equivalent definition of what I wrote earlier, A transpose A minus I divided by 2, that was a tensorial definition. This is for the initial notation for the same thing. If you expand that out, this is what you would eventually end up with in the simplest situation. So when you have this is very easy to see that, therefore gamma ji and gamma ij are equal to each other, which is what we meant by symmetry, and therefore reducing the 9 strain components or strain measure numbers into just 6. Again, I might be mentioning this quite a few times as either components or measure numbers, which are essentially parts of tensors. It could be a part of a vector, it could be a part of a second order tensor like what we are looking at. If you take a simple example of, let's say, a vector, let's say a force F is there, you know that it's can be expanded as F1 along, let's say, the unit vector V1, F2 along V2 plus F3 along V3, right? Now this is a vector F, and it's a first order tensor. That's why you have single underline to it. So what does this order actually mean? So a scalar is a zeroth order tensor, means it has 0 directions associated with it. The force is a vector which has one particular direction associated with it, which is the direction in which you are applying the force. Similarly, in this case, it's a second order tensor, which is why we would write gamma as with 2 underlines. 2 different directions are associated with it. It's very easy to see from the corresponding stress what actually it is. You're talking of the first of all identifying the plane on which the stress is acting through its unit normal vector, and then on that plane in which direction the stress is acting. So 2 directions are associated with it. Similarly, your E, that is the stiffness, or C, IJKL, is a 4th order tensor which we are associating with 4 different directions. Essentially, it's combining 2 different stresses, or one stress and a strain, and essentially each of them is having 2 directions associated with it, and therefore end up with 4. So just like we call the 0th order tensor as scalar and the 1st order tensor as vector, these second order tensors are typically referred to as dyadics. it's a special case of tensors, like where the order of the tensor is 2, and that's what we are talking about. Similarly, your CIJKL, which is essentially with 4 underlines, is what we typically call as a quartic to deal with the 4 different directions that are those are associated with that. Now, the reason that I'm bringing this up is to show that there are possibilities of other strains definitions existing. Many of those are also symmetric, and still what many of these things that we are talking about will be valid. But what is important to be noted is that once you introduce a particular strain definition, like what we have done here, which is called as Green-Lagrange, then you cannot use any arbitrary stress along with it. There's a particular stress that you have to associate with it. In other words, your SCD should not change, because your SCD is essentially half of your stress multiplied by your strain summed up over all the components, right? Now, what you have to ensure is that if you have chosen the Green-Lagrange strain, for example, you choose what is known as a particular stress tensor known as the second Piola-Kirchhoff stress tensor. So what this essentially does is that it's because remember that any stress is associated with a particular force and a particular area, right? So both being vectors. Now you are saying that in this particular case, both the force as well as the area are associated with the undeformed configuration. I'm trying to put this in very, very simplistic terms, not going into the details of the tensorial definitions, etc. In terms of the deformation gradient tensor that we introduced, there's no need to get into all of those complications, because most situations you'll be dealing with these two, this particular strain and this particular stress. So therefore, it's good enough for you to know about these two, and both of these are symmetric. And of course, in the case where there's no body moment distribution in that particular material, otherwise your the shear stresses, let's say for example a tau 1 2 and a tau 2 1 will differ. You have to look at the signs for that, but essentially this so this is what you will be talking about as the body moment associated with that particular direction, which is in this case the third direction. So similarly, when you talk about a tau 2 3 and tau 3 1, you would have the 2 m2 associated with it, etc. So there's a difference between tau 1 2 and tau 2 1. That's what we are saying. The complementary shear stresses are going to be different from each other by a body moment. And this is anyway moment, which is Newton meter, and it's a distributed moment, so it's per unit volume. So this is meter cube, and you would see that therefore 1 meter cancels with this, becomes meter squared. So this is same as Pascal's, which is what your shear stresses are as well. So what we have assumed through that assumption number 3 is that all of these m's, m1, m2, m3 are all 0, and therefore we are taking advantage of that, and that is what you have in the Piola-Kirchhoff kind of stress definition as well, that because it's associated with the undeformed geometry and with the force also. Basically, you're putting everything in terms of the coordinate system or the unit vector system or the reference frame, which is associated with the undeformed configuration, and therefore you're ending up with one of the simpler definitions of the stress tensor. So always remember that if you happen to change for some reason the strain definition, you cannot continue with the same stress definition, because those two together may not lead you to the same strain energy density, which is, remember, a scalar. So the scalar is independent of the reference frame that you have, so it has to make sure that for whatever combination you have, you end up with the same number for a particular configuration in which you're loading a particular structure. So therefore, at each point, because this is a density, it's a distribution, we're talking about the strain energy density at each point. So that has to be replicated when you change either one of them, because then you'll be changing the other as well. Okay. So are there any doubts on this? Okay. So let's. So now we have the next assumption that we have already from using all of these. We have said that our C, which can be reduced in the void notation to a matrix, which is a 6x6 matrix, is essentially consisting of your C11, C22, and C33, which are associated with the normal stiffness in the three directions, and then you have the shear stiffness, C44, C55, and C66. In those three planes, 2, 3, 3, 1, and 1, 2. Then you also have your C12, C13, C14, C15, C16. There's a reason I'm fully populating it. So now you have this, and we said that there are 21 constants associated with it, which are independent. And other 15 are dependent on the 15 that you have on the top of the diagram. Now, so far we have not made any assumption in terms of the material symmetries that could be possible. And composites luckily lead us to certain material symmetries, which is what we will take advantage of in today's class. What the first thing that is called is orthotropy, and the meaning of that is quite clear from the two parts of this word. The prefix is ortho, which is referring to perpendicular directions, and tropy means direction. So you are talking of the three perpendicular directions, which are principal material directions, along which, if you know the properties, you can get the properties in any other direction. So in other words, the general case of the complicated, when you go and say that it is a material is not isotropic, is what we call as an anisotropic material. An anisotropic material can have arbitrary properties in any direction. So any particular direction you want the property, you have to measure that. But here, the advantage with composites is that they are orthotropic. All that you need to know is in three particular directions, and if you know in those three directions, any other direction you will be able to get it. Now, what that also refers to is, this is equivalent to saying the material is triclinic. So those of you into metallurgy or other things, you would have probably explored this, monoclinic, biclinic, and triclinic. So essentially we're talking of three planes of symmetry. So that is why we call this triclinic. But the simplification that we are going to go for, we will see shortly, it doesn't need to be triclinic. Even if it were biclinic, you would end up with the same kind of simplification that we are going to do with this stiffness matrix. In other words, we are going to reduce this 21 independent coefficients to fewer, and that number, how many fewer that we are going to reduce it to, will be the same irrespective of whether there are two planes of symmetry or three planes of symmetry. And the planes of symmetry that we are talking about are material planes of symmetry. So in other words, at any given point in the material, there is a plane. So in other words, if I take at any parallel plane also, that is also a plane of symmetry. Unlike the laminate that we were dealing with, if we said something is symmetric, then at a particular height, whatever direction the fiber was, the same direction it has to be at the bottom we were talking about. Here it's not like that. It's essentially a reflection that is happening. And so if you are familiar with direction cosine matrices, there will be a rotation matrix that will be associated with this. And suppose we are reflecting it with respect to the 2, 3 plane, then this particular term would be -1. The others would be similar to an identity matrix. And this is the kind of transformation that would take place. But the quantity that we want to transform now, remember, even though we are writing it in the form of a matrix, we have to keep reminding ourselves, is actually a 4th order tensor. So the same thing you cannot directly use for that. There has to be a different way of approaching this whole thing. So we have to go back to our CIJKL, and if I want it in some other direction, let's say CMNRS, then I would get it in terms of CIJKL. And I would say that because this particular plane of symmetry exists, that is x2, x3 is a plane of symmetry. So x2, x3 is a plane of symmetry, which means that when you're having that as -1, you're essentially reflecting about that plane. So what we are saying is that this, if I want in that new system, that is only one of the unit vectors have changed the direction. In other words, your b1, which was parallel to your x1, I have made it as -b1. The others remain the same. So when that is happening, so I will have, because it's a 4th order tensor, I'll have to multiply it by r's elements 4 times, and each one of them is associated with an m, n, r, s, I, j, k, and n. And once again, you see that there is a repeated index of your ijkl, which means that there is a implied summation over I, j, k, and l from 1 to 3. And once you substitute for each one of them from this matrix, which is very simple, many of the terms will drop off because of these zeros that are there, and some will remain as they are because of the ones. Only few will change to -1, and then you will see that for this simple example that you have, you would end up with certain 0 quantities, and those will be essentially these off-diagonal terms. Okay, so these off-diagonal terms, you will see that you can actually expand this out and see when you because those two should be equal to each other, right? So even after the reflection, those two should be equal to each other, and that is possible because you will get this particular value. Remember that it's associated with the 1, 1 and the 3, 1. So if you were to expand this, remember, corresponding to this, you had on this side you would have sigma 1, 1 for the first row, let us say, and the last 2 terms that you would have over here are your sigma 3, 1 and sigma epsilon or gamma.
Three.
3, 1, 1, 2. Right? So these are the last 2 terms I'm writing. The first 4 I'm not writing over there. So because I'm talking about the last 2 columns of this, that's what it would be associated with. And on the left hand side, it would be associated with sigma 1, 1. So you're saying whether sigma 1, 1 will depend on gamma 2, 3 and gamma 3, 1 is essentially taken care of by these 2 terms.
It's a
Your
3, 1,
5 and
so 3, 1 and 1, 2, right? Last 2 are.
oh yeah. So the 4th one was gamma 2, 3. Thanks. So what we are talking about is these 2 columns are going to be multiplied by these 2 strains, and oh yeah, I forgot to mention the other thing I was trying to explain is the difference between measure numbers and components. Okay, so I started off saying that, but I didn't complete that. So we are essentially talking of parts of a particular vector, and for the reason I started talking about the vector, for example, f is equal to f1 v1 plus f2 v2 plus f3 v3. Now when we talk of measure numbers, what we are talking of are just this f1, f2 and f3 alone. Those are these scalar quantities that are the magnitudes in those three directions of v1, v2, v3. So your measure numbers for that vector are f1, f2 and f3. On the other hand, when you talk of components, you're actually talking of vectors. So in other words, the components that are there are this entire first term, that is f1 times v1. So your f1 v1 comma f2 v2 comma f3 v3. Unfortunately, many people even in the literature tend to use these two interchangeably, measure numbers and components, but always remember that components will retain the characteristics of its original parent from which it came. Because f is a vector, therefore your f's components should also be vectors. On the other hand, the measure numbers will always be by the very fact that it's a number, it's a scalar, so it's only talking of magnitudes in the different directions. So I'm giving this simple example with a vector. The same thing holds with your stress or strain, for example. You're talking of a particular gamma 11, then you're talking of a measure number. Whereas you put gamma 11 multiplied by v1, v1. Now I'm not putting a dot or a cross over here. These are juxtaposed next to each other because this is a dyad. This is what we call as a dyad. Just like you have unit vectors which are used to get your total force in a particular reference frame of coordinate system. Here you need to, as I said, two directions. One is associated with the plane of the particular stress action or the strain action, and then you're talking of on that plane what is the direction of the force that you're having, and based on that you have to have two quantities. So in general your gamma ij will be with a bi and a bj. Okay. So now this whole thing is a component of gamma, the original tensor that you had, which is gamma. It's a component of that. But if I don't show your b1, b1 and talk only about gamma 11, it's a measure number of the 11 measure number of your gamma. So you have keep that distinction very important, because the way you manipulate a lot of things will be very different depending upon whether you're dealing with measure numbers or components, because many of these measure numbers will be using a matrix formulation, will be putting it either in a square matrix or rectangular matrix like this, or a column matrix like this, and therefore the kind of manipulations that you do, always be careful what measure numbers are they, what was the original parent, was it a vector, was it a dyadic, was it a quartic. All of that will matter in terms of how you're going to eventually manipulate that. So just because you see a column matrix, it doesn't mean that necessarily it will get manipulated in a very similar fashion. So you have to make certain changes based on which parent it came from, and therefore in many situations the components become more important than the measure numbers. Okay. So we were talking about the orthotropy, and orthotropy we take to start with just one plane of symmetry, which means that what we call such a material as a monoclinic. There are very few natural materials which are monoclinic but not of much interest. So for all practical purposes, this is more of a theoretical thing that we, from a structural material point of view, we don't really need that. But to understand triclinic, which is what orthotropic materials are, we need to understand what is monoclinic, and that's what we saw, that if you had just the 2, 3 as the plane of symmetry, x2, x3 as the plane of symmetry, in other words, B1 was the normal to which that particular plane happens to be a plane of symmetry, then you see that because of the reflection that you have and you equate those terms, then you would get this particular thing to be 0, because you would end up with let's say your C1131. So 1131 is this particular term which we are calling as 15, right? So now you would get that to be equal to minus C1131 once you expand this out, because you would have seen that after performing that transformation about that plane on which you're reflecting it, you would get this particular result, which is possible, as you can see very easily, by only if that is 0, which is why all of these will end up 0. So I'm giving just this as an example, but that's the case that will happen with all of them. Similarly, once you have a second plane of symmetry, it's very easy to see that this along with something else will go to 0, and therefore already it's the effect of what 3 planes of symmetry would result in. Yes?
Material is given to me, how can I know that it is orthotropy without doing all these mathematics?
By testing. So you would test in particular directions. You would see that if whether you're, let's say, you have this, you're applying, let's say, a shear in this particular direction or a shear in the other direction, you would end up with the same set of results, right? So now what you're trying to do is that you're looking at what are the properties in 3 different directions. I can test and find out, and I can get the properties in any arbitrary direction as a function of those, and I can calculate that theoretically. I can also do another test, 4th test in that particular direction, and I will see that I can replicate that. So essentially you're saying that it's not infinite number of independent directions in which you have properties, but just 3 independent directions. If I have those 3 properties for any particular specific property, that same specific property in any other arbitrary direction, I'll be able to get in terms of those 3.
Usually the extension stresses will cause shear strains here.
That's correct. When all of these were fully populated, yes.
So orthotropic will not create.
Exactly. So orthotropic will not create that in those 3 directions, which are what we call as the principal material direction.
But in another direction,
it can still happen. Yeah. So you would still, in a generic coordinate system, you would still have a fully populated matrix even for an orthotropic material. But in those principal material directions, which is what we are talking about right now, you're right, we will have these as zeros. Okay. Because we'll be using a transformation of a 4th order tensor, and when we do that, even with all of these zeros, you will end up in general with non-zero values in the.
whether we can know easily we can locate the material axis if something is given to me. We can.
Something means?
Some like composite material is given to me.
Yeah.
Whether I can locate the material axis.
Yeah, see, because typically what you're doing, you're using in flight vehicle structures is unidirectional fibers. So you know that the fiber direction itself is one principal material direction. And therefore, the plane perpendicular to that is orthotropic, remember, they are all mutually perpendicular to each other. So that plane is also having, and in fact, we will go to another assumption, we will see that these materials are transversely isotropic as well. So in that plane, doesn't matter which 2 axes you take. So the only axis of identification is that fiber direction. You could also have certain other applications in aerospace which are also quite a large quantity, where you have fabrics. So again, in the fabric, those 2 directions of the fabric weave become essentially your principal material directions, and perpendicular to them is also a principal material direction. So it's quite easy to identify. But when you have, let's say, short fiber composites randomly distributed, etc., then it becomes a little more of a challenge. You may not have that. But the fact that it is so randomly distributed beyond a certain level of randomization, that becomes almost like an isotropic material to handle. So most of those materials are treated as isotropic materials. You measure property in any one direction, you use the same property in the other directions.
Same for the laminate or the laminate?
Yeah, very good question. So this is an example that you see over here, where you have fibers which are running parallel to the breadth and the topmost layer, and here it is at a different angle that you see over here, and in the bottommost you are seeing it 90 degrees, right? So now when you're dealing with it, that's why we talked about 3 levels of dealing with this. One is the micromechanics, the mesomechanics, and the macromechanics. So in the micromechanics, what we will do is each layer we will replace it by an equivalent homogeneous material, fictitious material of certain properties, and then you will stack them up, and then depending upon whether it is a plate-like structure or a beam-like structure, we will reduce it. So let's say it's a plate-like structure, then instead of having these n number of layers, I will have just one layer, which is another fictitious material made out of these fictitious materials, and whose properties I can determine mathematically by just integrating over the thickness direction. Yeah.
Sir, we know that like when second order tensor is acting on a vector, we do matrix vector multiplication. For if fourth order tensor is acting on second order tensor, how to do mathematical?
Yeah. So essentially, let me take that same example which you talked about. So you have, let's say, a vector dotted with a diagonal, which you said you can do a manipulation like that. So this is what is a dot product, right? So you have an extrapolation of that dot product. In the case of, let's say, two second order tensors, let's say things that we know, you will have two. So essentially, just like in this case, you are going from 3 to 1. This will end up with some arbitrary vector that you would have, because you are essentially reducing with respect to or contracting with respect to one of the indices. Here you are contracting with respect to two of the indices, and this is very similar to your matrix multiplication. So you see that will essentially lead you to that whatever. So here, if it's a single reduction, then you will have one reduction. Otherwise, if it is two, then you will end up with two. So that's how you will end up. So it all depends upon generalizing your dot product into higher dimensional dot products.
So I'm asking like CijKL, when we are CijKL is acting on epsilon KL,
Okay.
then how we mathematically do that? CijKL, it's difficult to imagine like fourth order tensor.
Yeah, but once you have it in the initial notation, this is your sigma ij, right? All that you have to do is to have an implied summation over this, right? Your k and l are getting summed over 1 to 3.
Okay.
You cannot imagine this as a matrix because it's a 4-dimensional matrix. It's not a planar matrix like what we write, which is essentially a 2-dimensional state, right? So this is 3, 4. At least you can imagine, let's say, say a third order tensor. So now you can see that you can think of it as a matrix, and then also along the length of this room, you're again stacking more matrices. So essentially, you're coming up with that. Whereas this is something difficult to imagine what it will look like. But the very fact that you have a summation over that, your mathematics or computations is quite straightforward to do. Right?
Oh.
So this is what we mean by two dots over there, because two indices are getting removed. So those indices which are getting removed are essentially your dummy indices, right? What we call as whereas these are fixed, they are free indices. For a particular stress, let's say sigma 2, 3, I'm trying to calculate, then this also gets fixed. So whereas the others are roaming around, and you have to take all of them in account. Discuss this. So orthotropy. So we saw that in general what would happen is you would end up with, once even two planes of symmetry are taken into account, you would have all of these would become zeros, and it would be symmetric like this. Okay. So we saw that when one plane of symmetry, two of the rows except the diagonal terms, everything was going to 0. So it's very clear to see that once another plane of symmetry, which is perpendicular to the first one, is introduced, the other one will go away as well. So what we are talking about is that when you have zeros over here, there are two types of zeros. One is a submatrix over here, and there is a triangular over here, which is also a set of zeros. Now, this zero, what it is essentially saying is that there is no coupling between the normal and the shear. So in other words, I apply normal stress, I should not get a shear strain, and vice versa, right? So that's what this zero refers to. And what this zero refers to is that if I'm in those principal material direction, which is again the condition I should have mentioned there as well. So then you would have a shear in one plane, one of the principal material planes will not, a shear stress in one principal material plane will not cause a shear strain in any mutually perpendicular plane that is there. So in other words, let me take a cuboid like this. And suppose use coordinate system as well. Okay. So now you have, let's say, in the x1, x2 plane, I'm applying a small element over here. I'm applying the shear stress, which is tau 1, 2, right? So now I'm saying that this cannot cause a gamma 2, 3 or gamma 3, 1. These will be 0, right? If this is the only stress that I'm applying, I'm not applying any other stress, then at that particular point, you will have these two going to 0, which is what this particular thing refers to, okay? Whereas this, what it is saying is that when I am applying tau 1, 2, I cannot have my gamma 1, 1, gamma 2, 2, and gamma 3, 3 either. So those will all be equal to 0 as well. Also, so this is what this 0 is essentially. Right? So this one is using that R matrix which I talked about, which for the first plane was with the 1, 1 element minus 1. For the next plane, it will be the 2, 2 element and 3, 3 element respectively. And once you have all of that, you will get all of these as zeros. So one way of reasoning is by using that R and actually expanding that out and seeing what happens. The other way is also you can use a just an intuitive explanation using physicality, that you are saying that you're applying sigma 1, 1, you should not get a shear in the other plane, because if you get, it should be such that it should be the same on the top and the bottom, or on either side of the x1 plane, which is your x2, x3 actually, perpendicular to b1. So that particular plane, you can see that if you should have non-zero values, they should be equal to each other, which is not possible because they will be in opposite directions on either side, and therefore they are equal to 0. So you can have either a math-based argument or an intuitive physical-based argument. Both will essentially lead you to the same result, that these are 0. So I would encourage you, not a homework, but you can just check, you can go back and check what exactly happens. If you have any issues in understanding that from an intuitive physical perspective, you can tell me in the next class, and we will I'll try to describe that. But it's quite straightforward to see once you understand what I'm talking about. Okay, so it will be a good exercise just to jog your skills in terms of the symmetries and things like that, and you will see that there are two equivalent ways. One is a mathematical way, the other is a physical way of reasoning it out. The fact that all of these decouplings are happening between shear on the one hand and normal on the other, and between the shears themselves. So as he pointed out, this particular thing is valid only when your x1, x2 and x3 are principal material directions. And therefore, we call this particular thing as what it's called as a special orthotropy. So special orthotropy is only in the only case where you would have all of these as zeros for sure. Whereas the situation where I introduce some other arbitrary coordinate system over here, which is also a Cartesian coordinate system in the sense that it is mutually perpendicular and unit vectors are parallel to each one of them, which I call as, let's say, y3, y1, y2. Now, for the same material, you will have a fully populated matrix in general. Okay, so because but still the number of independent coefficients will still remain the same. So let's now check out the independent coefficients. You have the 6 on the diagonal and 3 off diagonal. So total of 9. 6 plus 3 equals to 9 independent coefficients. Remember at this stage when we had just 4, we had 21. Remember 21 independent coefficients. Just this one assumption of orthotropy has dropped it further from 21 to 9. Okay. In between you would have had, with a monoclinic you would have 13, etc. So that's not of much practical importance to us. It's only of just theoretical knowledge. So this 9 independent coefficients are what you typically need in any three-dimensional composite, especially when you're dealing with, let's say, commercial finite element software and things like that. You might have to feed in these values. If you're doing a full 3D analysis, then you need to know the properties in all those directions. Now, whether it is in the principal material directions and therefore called specially orthotropic, or in a general direction when we call it as general orthotropy, in either case, the number of independent coefficients will still remain 9. It's just that the number of non-zero coefficients will change from, in the specially orthotropic, you have 6 plus 3 plus 3, because there are 3 on the other side of the diagonal as well. So you have total of 12, right? So 12 non-zero coefficients in the specially orthotropic case, and in this you will still have all your 36 non-zero elements in general. Right? So is this clear from the orthotropy perspective? Then we will go to the next one. So that's transverse isotropy, as I already briefly mentioned earlier, that if you take this top layer, for example, and I take a plane which is along this, which is along the length and along the height, then you see that there is a plane of isotropy. So now that's what we call as transverse. So because perpendicular to the fiber direction, you are having, so when you have a fiber and all fibers are running parallel to each other in that particular layer, then you see that already we have introduced the principal material planes as x1, x2 and x3, right? Now if you look at that x2, x3 plane, whether it is x2 or x3, both are directions which are perpendicular to the fiber, and therefore we typically call this as xt and xt prime. I think I mentioned this in a previous class as well. So to distinguish between the two, but essentially they are both transverse direction, and this is of course xl, which is your longitudinal direction, right? So now already with just orthotropy alone, we saw the reduction to 9 independent coefficients and 12 non-zero in the specially orthotropic situation. Now with this transverse isotropy, we're going to get further reductions. So let's rewrite what we had at the level of orthotropy. We had C11, C22, C33, C44, C55, C66. So this is what we had already. Once we had made these 5 assumptions, we had ended up with this in the principal material direction. Always important to qualify that, because otherwise you can have it fully populated. Okay. Now we are bringing in this transverse isotropy as the 6th assumption that we have over here, and once that comes in, we see that your 2 and 3 directions are very similar to each other, which is what we are calling as T and T transpose, right? So these 2 and 3 are essentially interchangeable, and therefore, for example, you would have your C22 is equal to C33. So you already have one reduction that is coming over there. Similarly, if you look at the first row, your C12 and C13, the first term in both is, first index in both is 1. Only the second index is changing, 2 and 3, and therefore these two are equal to each other. So I have one more reduction. From 9 I got to 8, and from 8 I got to 7 over there. Now if you look at these two, these are associated with gamma 31 and gamma 12, the last rows and columns, right? And correspondingly, of course, on the other side you have sigma 31 and sigma 31 and sigma 1, right? Now you see that here also, because again already we have said that the strain itself is symmetric by definition. We are using green Lagrange strain. Similarly, your stress is also symmetric because of no body moments. So it doesn't matter whether I write 3 1 or 1 3. So in both these cases, one of the indices is 1 already. The other index is 2 and 3, which means that these two have to be equal to each other. In other words, the shear stiffness in that transverse plane we're talking about along with the longitudinal plane. So in other words, your XT XL plane and also your XT prime XL plane. So these two planes are behaving in a very similar manner as far as the shear loading is concerned, and therefore I have one more reduction which is coming out of this. Now, if you remember, you can take advantage of another thing that you know in isotropic materials. In isotropic materials, we know that even though we typically use 3 different material properties like G, E, mu, or sometimes of course we use the bulk modulus as well as along with it. Now, out of these 3, we know that only 2 are independent from each other. In other words, your G we can show is equal to E by 2 into 1 plus mu, right? Now this is irrespective of direction, this is for a pure, fully isotropic material, right? Now we don't have that luxury over here. What we have is only transverse isotropy. In other words, that particular plane, there is an isotropy that is involved. So any shear modulus that is involved with that particular plane can be related to the Poisson's ratio and the Young's modulus in that particular direction. So in other words, if I write this as GTT prime, I would have it as ET and I would have it as mu TT prime, right? And even though in general it matters whether I take which I put first, because the first one is the input and the second one is the output as far as Poisson's ratio is concerned. Here it doesn't matter because both are transverse directions. Here it doesn't matter. And for shear modulus, always it doesn't matter, because always the remember the shear strain is defined as the change in the 90 degree between two planes. So even in LTA, for example, you can write it as TL, doesn't matter as far as the shear modulus is concerned. But only with Poisson's ratio, you have to be careful that which direction are you applying the load or stress, and therefore which direction are you measuring the strain in, and those two strain ratios is what you are essentially talking about. You would remember this well because you have done a homework related to new LT, trying to get new LT, so you would know what that order actually, why it is important. But here this is the case as far as T and T prime, because of the transverse isotropy, it really doesn't matter if you interchange. But this always, whether it is LT or LT prime or TT prime, all these can be interchanged with each other, so it really doesn't matter. But this particular equation is not valid once any of these change to L. So in that plane, you know there is no isotropy. Any plane which is not that TT prime plane or X2, X3 plane, you will have anisotropy coming in, and therefore this particular equation is not valid. So what this can be equivalently stated in as is that your C44 is going to be given by your C22 minus C23 divided by 2. So this particular thing, you can show that essentially your shear and your Poisson's ratio and your transverse stiffness are all related to each other. This is that particular equation. So this will be your homework, number 5, where you can prove this. You can go back to your strength of materials and see how you had proved G is equal to E by 2 into 1 plus nu, the simple thing. Exact same thing you will see. That is what you will have to do, the same steps, and you will see that this can be shown as well. Now, the important thing is to see the number of equations that we have got. 1, 2, 3, and 4. Okay. So remember that we had 9 already, 6 on the diagonal and 3 off diagonal, which is repeating on the other side of the diagonal. Now we have these 4 equations, and therefore you have only 5 independent constants that are left. Okay. Once you do tests to determine these 5 independent constants, you can get everything else, even in other directions, non-principal material directions as well, through just manipulation using the direction cosines associated with the new coordinate system. You can use that to get that. So this is all that is required. So remember, we started off with 81 constants, even after introducing material linearity, and that we have brought it down. In the most general case, of course, when you do not have material linearity, you don't even have constants to start with. Okay, those are functions in general, and those have to be determined using many more variables, and it becomes a little more complicated. But in the case where you have linear elastic material, you started with 81, and the other 4 assumptions that we made led us to just 5 of these. Now, though we have been talking in terms of C, this is useful when we are dealing with mathematical manipulation of these matrices and for those kinds of situations. But in a test, how do you determine these? You do not directly go and determine the C's. Instead, you determine the quantities which are associated with applying a stress in a particular direction and measuring strains in all the other directions and getting those matrices populated. That particular matrix is not the stiffness matrix, but your compliance matrix, which is nothing but the inverse of this. Right? The stiffness and compliance are inverse of each other, and very strangely, for some reason that I'm not aware of, typically you refer to stiffness with a C, and the compliance is usually denoted with an S. They are interchanged for some reason in many textbooks. So that's the same notation, terminology that will be following here as well. Now let's see what those 5 independent coefficients are. Already you would have probably looked at from this. You already have, let's say, along the longitudinal direction you have EL, then you have your Young's modulus in the transverse direction, then you have one of the Poisson's ratio nu dt prime, and then you have one more which is nu lt, which is not related to this, and then you have your GLT. And if we remember our first few classes on micromechanics, we already derived an expression for this, and then you went and did a homework for this, which turned out to be very similar to that. Then in the second class on micromechanics, we derived this in the class, and then you did this, right? GLT is what you got. And that, again, a reciprocal relationship was there for that. Now, the only thing that we have not dealt with is this particular thing, your nu tt prime, or equivalently your gtt prime, which is essentially in the plane of isotropy. What is the shear modulus or the Poisson's ratio? And that is typically matrix dominated. So even when you use the rule of mixtures and try to derive that, you get a relationship which is not of much use. So many people just take the matrix Poisson's ratio which is of course an isotropic material, or the shear modulus of the matrix to be that of the composite as far as that transverse isotropic plane is concerned. Now it's very easy to see because in that plane, remember, the fibers are all having a circular cross section. Now if I apply a shear load to that, these just tend to rotate and they're not offering much of a resistance. So essentially it's as much resistance as your matrix is offering, whether it is in shear or when you're talking about the Poisson's ratio, you are trying to pull it in one direction and seeing what happens in the other direction. There's not too much of a contribution coming from the fiber, which is having a cross section which is circular in that plane. Whereas in the other plane, your LT plane, you see that the fiber that you're now exposed to is not just circles, but essentially you're having a straight line which is much longer. In other words, your dimension is involved is much longer. So now if I apply a shear to this, there is some resistance that the fibers are offering as well, which is what we looked at in our derivations as well. But again, there also we saw that it all matters in terms of the volume fractions. If you have very large volume fractions, that's where the reciprocal terms are going to have contribution from the fiber. Otherwise, it's mostly matrix dominated there as well. Because you're talking of reciprocals, you're talking of the quantity which is larger is actually going to have a lesser contribution, which is what is happening where that the fiber is not contributing much, whereas the matrix, because it is a smaller Young's modulus, it's in the denominator because of reciprocal, therefore it is contributing much more and therefore it is dominating that. So of course there are more advanced micromechanics models also which will take into account the fiber contribution, but all of those are beyond the scope of this particular course. But it's very important to understand that those 5 that we have reduced to, one from the matrix perspective, you have seen in that, which I can remove because they are equal to something else, and then in terms of what are known as engineering constants. So these are engineering constants because why they are called engineering constants is these are the ones that we will actually determine in an experimental test, and when we perform the test we will know what kind of loads we are applying in different directions, we will measure the strains in different directions and we will plot them against each other, we'll measure the slopes, and from those slopes these will be direct fallouts, and from these then we can go ahead and calculate that. And even then it's much easier to deal with the compliance matrix than with the stiffness matrix, and that's because of a reason, because of the way we perform our tests. When we perform a test, let's say a uniaxial testing machine, what do we typically do? We fix one of the ends and we apply a tensile load at the other end. We're trying to pull it, right? So in other words, we are applying a sigma 1, okay? If 1 is the direction along parallel to the specimen. Now you're applying sigma 1, but you're keeping all the other stresses equal to 0. Sigma 2, sigma 3, 2, 3, 1, 2, all of them are kept to be 0. But the strains are not kept to 0 because they are free to expand or contract, and therefore you would have all the strains in general present. Even in an isotropic material, you would see that the Poisson's ratio will make the other directions contract. So it's not possible in an experimental setup to easily control or keep 0 the deformations in the other direction. But it's very easy to keep the stresses 0 because just not apply any boundary condition there, it's just allowed freely to move. Because of that, you would see, because remember that the stiffness is given as sigma is equal to C times your gamma, right? So now, if I apply only one of the sigmas and try to calculate, it's very difficult to populate this matrix. On the other hand, let's look at the inverse of this, which we saw as the compliance matrix. Now if you look at it, the right hand side that I have, I can apply it one term at a time. So I start with sigma 1 alone. Only the first row of this matrix I need to, the first column of this matrix. The first column of this matrix, yes, I need to get. Of course, it's a symmetric matrix, so the same thing holds as far as the row is concerned as well. But I can measure all of these gammas by putting strain gauges of property. For shear strain also, there's certain bridges that you can do to get those values as well. Once you get the gammas and for a sigma 1 and you change the sigma 1, you keep changing within the elastic limit. And then you, once you get that straight line, you would see that all of those first column of this, that is your S I1. Right? So your first column of that will get populated, and because of that, your first row S1I will also get populated. So that's how you populate S, and once S is populated, then you can calculate C as the inverse of that S. It's much easier to do that. Instead of directly determining C in an experiment, it's usually the compliance or S that is determined, and then you mathematically calculate the C through an inverse. Okay, so I think that is clear. So let's just write that in that particular fraction. You'll see a new thing that I'm introducing, that a factor of 2 on the shear strains over here.
How long is your class?
It's still 3:30. Yeah.
Thanks.
So we see that we are introducing this factor of 2 over here, and that factor of 2 is 2 because, as I said, now what we are going to be talking about is experiments, right? And in experiments, essentially, it's engineering that we are going to be dealing with, and therefore we talk of engineering strains now. As far as normal strains are concerned, there is no difference, but the strains associated with the shear, they are different, whether it is engineering strain or tensorial strain. So that's why we need to bring in this 2 explicitly. It doesn't matter, all that you're going to do is a manipulation in your C so that the 2 factor gets absorbed in some way. The equations still remain the same. Now this is equal to sometimes tau is used, of course, for the shear stresses. These 3 are written as tau 2, 3, tau 3, 1 and tau 1, 2. We are following a consistent notation over here. So now what's going to happen is, in one test, it's a uniaxial test, let's say, I'm applying only sigma 1, 1 and keeping all of these quantities as 0. So I'm applying that, and I'm using strain gauges to measure these and then plotting them versus each other, those straight lines, and measuring the slope. So then what I get is the first term becomes just 1 by EL, right? So the second term becomes minus nu LT by EL, and again minus nu LT prime, which is also LT, by EL, and I'm going to get these as 0 because of that orthotropy that we saw. That same thing is going to come over here as well. You can actually do the measurements and see that they will end with 0. So this is how you populate the first row. Similarly, you can go about populating the second row as well. For example, you will get 1 by ET over here, and then you will get the others as well, 1 by GLT, etc. So for this, for example, you would have the 2, 3, which is your 1 by GTP, right? So, because associated with 2, 3, right? So, whereas these will be 1 by GT. Right? So, you would see that those 5 constants that we were talking about, those are the ones which are going to be populating this. And this is the simplest way in which you can write, and you can also understand what exactly is happening in terms of the physics of what is contributing in terms of your fiber or matrix, and all that dynamics that is happening within them. You can much more easily visualize that. It's a much simpler compact expression that you have over here. But if you invert this and actually, so this is your compliance S, this matrix, right? So it's 6 by 6 matrix that you have is your compliance S. Once you get this, you can invert that to get your stiffness matrix C, and you will see that that's much more complicated compared to this because it's going to involve denominators with the Poisson's ratio squared, etc. All of that is going to make it a little more complicated. Of course, these are just become the reciprocals of that. That would be much simpler, but just we're talking of a fully populated 3x3 submatrix that is there, which you have to invert in order to get your C populated. Okay. So thank you. So with that, we'll stop today's class with transverse isotropy. We will take up further assumptions, actually accumulate further assumptions as we go in the next class.